Okay, so today we're going to talk about solids handling, and this is our seventh session in our Tribal Wastewater Operator Certification Series. We're with the Southwest Environmental Finance Center at the University of New Mexico. So AJ and Matt are here, and they are in Albuquerque, and I am in Billings, Montana. So yeah, that's me. I'm a research scientist here at the Southwest Environmental Finance Center at UNM, and I've been here for I don't know 3 or 4 years now. And I used to be a drinking water operator at the Bozeman, Montana plant. Also on today, and going to do the second part of the webinar is Matt. Matt, if you want to say hi.
Hey everyone, Matt Ziegler here. I'm the Tribal Water Utility Program Director at the Southwest EFC. And if you need any help with anything, assistance, training, water, wastewater, let us know. We'd be happy to help. Thanks, Tucker.
Thank you, Matt. And then AJ is also on today. And AJ, if you want to introduce yourself really quick.
Yeah, hi guys. I'm a former wastewater operator at the Albuquerque Water Authority plant, and I'm a research engineer with the Southwest Environmental Finance Center, and I'm just kind of here to help with questions that kind of pop up.
Yeah, thank you, AJ. Yeah, so Matt and I are going to be doing the training today, but AJ will be around, and I think Mike Rivera is also on too, and they are both certified wastewater operators, so they have lots of experience with this type of stuff, more experience than Matt and I do. So if you have any questions, please put in the chat, and one of us will be able to answer your questions. And if we don't know how to answer your question, if we don't know the answer, we'll find an answer and get back to you. Okay, so as I mentioned, this is the seventh session in our wastewater operator certification webinar series. And so today we're going to talk about solids handling and land application. So please join us for our next two. We're going to do disinfection after this, and then an advanced wastewater math that's going to build off of our previous wastewater math session. And then lastly, we're going to talk about regulatory requirements, lab procedures, OSHA, and safety and stuff like that. So please join us for those next few. Okay, so for today, our agenda, we're going to talk about sludge thickening, the dewatering process. Then we're going to go into the digestion process. So the digester basics, aerobic digestion, anaerobic digestion, and then land application. So what you do when those processes are all through. Okay, so I'm going to back up for a second and we're going to do some review of the wastewater treatment process because I think it's nice, at least for me, to kind of get my brain situated of like what we're going to talk about today and where these processes fit in. So you can see in this schematic up here the processes that are associated with wastewater treatment in like a conventional treatment plant. So if you look over here on the left, this is where the plant influent, where the water is coming in. So this is our raw sewage over here on the left, and then it's coming in and then first goes through preliminary treatment, which is things like the screen, like the bar screens, the grit removal. So these big chunky solids like any rags or things that can get screened out. And then it goes through primary treatment, which is when the biosolids settle out. So the heavier things, they'll settle out into the bottom of the chamber. And then it goes through the aeration tank, where oxygen is added, and that really removes a lot of the chemical constituents like nitrogen, phosphorus, and such. And then it goes through secondary clarification, where that stuff settles down. So that's mostly bacteria and microbes at that point. And then goes to disinfection and then discharging. And so you'll see that we have all this whole other process down here at the bottom, the solids handling process. And so this incorporates the primary sludge from that primary treatment. So this is what settles out in those sedimentation basins or those clarifiers. And then we also get some of the sludge from the secondary clarifier. And this sludge, it's broken up into two channels, two streams. So we have our return activated sludge, the RAS, and the waste activated sludge, the WAS. WAS or WAS, however you want to pronounce it. So this is our overview of the wastewater treatment process. Okay. So just to talk a little bit about the preliminary treatment, really quick, because this also has to do with solids. This deals with solids that are a little bit different, though, because today we're going to talk about the biological solids, where the screening process and the grit removal process that mostly deals with inorganic stuff, things like bags and rags and gravel and sand and stuff like that. So that's all the stuff that is removed through the coarse screenings, the fine screenings, that grit removal, um, that kind of settling, and through some of these mechanical means like the cyclone separator or this like grit washing device. So those settle out in that preliminary treatment, and then they're disposed of in either a landfill or incinerated. So these are mostly inorganic materials, like I said, things like rags, plastic bags, all kinds of different junk. I'm sure you've seen it all if you work at a wastewater plant. So that's not what we're talking about today. That's what we covered in a previous session. Today we're going to talk about these biosolids. So this is the organic matter, so biosolids. So these are solids that are are coming in and is going to constitute is going to turn into our sludge. Okay, so if we look back at our schematic, we are today going to talk about this box down here that is highlighted in this gray. So our solids handling process. And here is where all that sludge comes from, which I talked about a second ago. So we have a few different streams of solids, of these biosolids that are going into our solids handling process. So we have our primary sludge from that primary treatment, those clarifiers, that's coming in here, as well as our waste activated sludge. So we have two different streams of biosolids coming into our solids handling process. Okay, and again, this is coming from our primary clarifier, so that looks like this. This is that primary treatment, also could be round, but this is where you get really high total suspended solid. So this is pretty much raw influent, minus those screenings and grit removal. So there's a lot of stuff in here, a lot of fecal matter and just things that are suspended in the wastewater stream. Then we also have our secondary clarifier, the waste activated sludge that's coming from here. So this is going to be not as high total suspended solids, and so we're not going to get quite as much sludge coming from here. And some of the sludge that comes out of the secondary clarifier, the secondary treatment, it's also recycled, that return activated sludge that we talked about during our last session. So that's where this sludge is coming from that we're going to talk about today. Okay, so today we're going to talk about this gray box down here that I mentioned, but this is one box in this schematic, in this diagram, but really it's a whole bunch of processes. So if we just break that box, spread it all apart, these are some of the components that make that up. So over here on the left is where we start again. And so we have that primary sludge and that waste activated sludge that's coming into this process. And then we have this thickening process, and this can be through a number of means. Then we have our digestion phase, and this is what Matt's going to talk about later. And then we have the dewatering phase. And so throughout this process, things are broken down more and the water is removed from these solids. So the idea is that we want to remove as much water as we can in this thickening process and the dewatering process, because it's less mass and volume that we need to then dispose of. And so through this process, in the thickening process and the dewatering process, which is what I'm going to talk about, there's also water that comes out of that. So it separates those solids from the water, to the extent that it can. And then that water is recycled and goes back to the influent of the wastewater plant, typically where this goes. And this is just one layout of this process. So not all facilities are going to have each of these different steps. They could be in different order. Maybe they are missing some of these. And so a lot of smaller plants especially may not have a digestion phase, or maybe not have a thickening phase, So just know that not all of these are necessarily required, but if you are at a larger plant, like the one in Albuquerque, for example, they have all of these phases. So we're going to talk all about all of these phases today. Okay, so we got our first poll question, and this is just to get an idea of how familiar you all are with these processes, or if you have any of these at your facilities. I know a lot of you have lagoon systems, and so, um, but some of you probably also have traditional treatment plants. So, let us know what you have interacted with before, just so we have an idea before we get going. I'll give you a few minutes. And this is a select all to apply. Hopefully you saw that. Okay, looks like most people have answered that. Okay, so I'm going to end this poll and I'm going to share the results. Okay, so you should be able to see that now. So it looks like some of all the above. So looks like a lot of you haven't interacted with any of these. So E was the most common answer, but every one of the other answers has somebody that's worked with that. So that's great to know. So thank you for filling that out. And then even if you have a lagoon, sometimes you still are doing solids disposal. So sometimes you have to pump out the lagoon, what's settled in that lagoon every once in a while too. Um, so maybe some of this will be relevant for you too. A lot of time the contractor will do that though. Okay. Okay, so these are the processes we're going to talk about, and I mentioned these a few slides ago, but just to give you an overview of what these are. So thickening, so that is going to be the first process we'll talk about, and that's more to reducing the sludge volume. So it's removing water from that sludge. So it's a higher percentage of solids versus liquid. So it's decreasing the volume, less to deal with. Next is digestion, and Matt's going to talk about that. So that's breaking down the sludge with microorganisms through that biological process. And then the dewatering phase. So this is removing more water from those solids. And instead of turning it into a sludge, it turns it into more of a cake. So it's more of a solid. And then the disposal and reuse. And that's the end of the line, getting rid of what you're left with. So because of like the similar concepts, I'm going to talk about thickening and dewatering, and then Matt's going to talk about digestion and disposal or reuse. Okay. So first we're going to talk about thickening, and it's exactly what it sounds like. It's thickening up the sludge into a consistency that is thicker, more solids versus liquids. Okay, and so why do we want to do this? So if we think about our sludge, so this is sludge from a primary treatment, so primary clarifier, that the sludge that's coming out of the bottom of that settles out. So that sludge typically contains about 95 to 97% water. So only 3 to 5% of that is actually solids. So we're trying to remove the solids from our wastewater stream, but then that sludge is still mostly water. So that means for every pound of that primary sludge, every pound of those solids, that's between 20 and 30 pounds of water that come along with that. So still a huge amount of water. So that's what we're trying to reduce. We want to thicken that so there's less water versus our solids. And then if we look at secondary sludge, so this after our secondary treatment, this is even less dense. So that is between 2% to 1% solids. So that means for every pound of secondary sludge that it's suspended between 50 to 100 pounds of water. So if we're trying to get rid of the solids that we're taking out of our raw water stream, there's a lot of weight and volume and mass that we're trying to get rid of that still is water. So we of course want to decrease that amount of water because it's a lot to deal with. And so that's why we do this thickening stage. All right. And so if we think about the next step too that Matt's going to talk about, if that amount of volume with the decreased thickness was going into our digestion step, it would mean that we would need a lot bigger equipment for the digester. So if it's less dense, we just need a lot more bigger equipment. So through thickening, we can actually improve our digester performance because there's a lot more stuff in there, solids versus water. It means we have lower construction costs because we don't have as much volume going into that digester, so it's going to be a lot cheaper to have those facilities. And then lastly, if you happen to have a digester that's heated, you're going to have to use a lot more energy to heat that up than you would if there's a less decreased volume in there. Okay. So for that concept, we're going to kind of go through that concept, but we're going to look at the numbers that are associated with that. So here's an example, and we're going to do some math here, but we're going to do it together. Don't feel like you need to do this math on your own. It's just going to go through so we can kind of look at the numbers of how this plays out. Okay, so in this example, I'm going to read this off. If a primary clarifier produces 3,000 gallons of sludge per day with a solids concentration of 3%, what is the weight of the solids produced per day? Okay, so if we go through our um, we can find a formula for this. I don't know if this is on your on that formula sheet that you get with the exam or not, but this is the formula you would use to figure out the weight of that dried sludge. Okay, so if we use this equation and we plug our numbers in, so we have 3,000 gallons per day of sludge. And then this 8.34, this is the weight of water. So for every gallon of water, it weighs 8.34 pounds. And then we have our 3% sludge. So that's 3% of the volume of that is going to be the actual solids. Okay. And that 8.34, that's the weight of pure water. And of course, sludge is going to be slightly more than that because there is sludge in there, but it's going to be pretty close enough for our calculations. If you wanted to know the actual weight of your sludge, you could take a gallon of it and put it on a scale, or you can figure out the specific gravity of it and then have a ratio compared to water. So, but we're going to use 8.34 for that. Okay, so if we cross out our units and then we calculate that out with a calculator, that 3,000 gallons of sludge per day is going to turn into 750 pounds per day of solid sludge. Okay, so that's what we have to get rid of. And so that's we can think of that too of our raw wastewater coming in per day there's 750 pounds of solids that we need to remove and dispose of. So say we are able to increase that percentage of the concentration of our solids or of that sludge to 5%. So say we do that through a gravity thickener or something like that. So as opposed to 3% solids, now we're up to 5%. So let's do that same equation and figure out what the amount of difference that would make in terms of volume. So we're going to use the same equation that we had in the last slide, but we're going to do it a little bit backwards because we're going to start with our 750 pounds of solids per day that we need to remove. And so I'm going to put that over here on the left. And then we have the rest of the same equation. So we are going to figure out what is our sludge volume. So if we rearrange our calculation or rearrange our equation, excuse me, and then if we calculate that out with our calculator, that's going to come out to 1,800 gallons per day of sludge. So that's the volume that we're going to have. And so we started out at the beginning, remember, with 3,000 gallons per day of sludge at 3%. And now, if we can just increase that concentration up to 5%, that almost cuts our volume that we have to deal with in half. So from 3,000 gallons per day to 1,800 gallons per day. So a pretty big difference there. So even just going 2% thicker makes a big difference. Okay. So how do we achieve this? So there's a bunch of different ways that we can get there. And so we're going to go through all of these in more details, but we're going to talk about gravity thickeners, um, dispersed or dissolved air flotation units, belt or fan presses, centrifuge, phase separators, and drying beds. And Matt's really going to talk about drying beds more so, but really the idea of all of these is to remove water from our sludge to increase the amount of solids in the volume of sludge that we have to dispose of or that we have to deal with. Okay, and a lot of these processes, I think, yeah, pretty much, I think all of them, they can be enhanced with polymers. So they don't all require polymers, but if you use a polymer with them, they're going to make them work better and more efficiently. So we talked about polymers during our primary treatment because they are sometimes added, or I guess they're well, I'm sorry, I'm thinking about drinking water now. So drinking water, they're added for the flocculation um, phase, but in wastewater, polymers are usually used just for this process. And so polymers, what they are is it's a long strand that has a bunch of positively charged like ends to it. And so you can kind of see that in this diagram up here. And so most of the solids, the sludge that's coming in, it has a negatively charged, or those sediments have a negative charge to them. It's the same with like drinking water coming into a plant. If you're if you're filtering out drinking water, and you're using a polymer for that, that also usually has a negative charge. So typically, when it comes to water treatment and wastewater treatment, these polymers are usually positively charged because you want to bring together those negatively charged particles. So if you use polymer, it's going to look something like this. If you use it for wastewater, it's kind of like a white liquidy goop. It kind of seems like Elmer's glue and it's very slippery. If you spill it, it's kind of a pain to clean it up because it's super slippery. And so these are typically proprietary. They um, they won't say exactly what they are when you buy them. They'll give you an idea um, of what it is on that SDS, the safety data sheet, but it probably won't say exactly what it is. Um, and so when you order this, though, it's usually pretty concentrated and it can come in powder or liquid form, and you usually dilute it into the concentration you want, and then you send it into the process with a chemical feed pump, just like you would with chlorine or any other chemical. Okay. And then to determine how much you need, you can do some bench testing with that. So put a little bit of polymer with different samples and mix it up and see what concentration works the best. Okay, so then the first equipment that we're going to talk about is gravity thickeners. And so this picture is a gravity thickener that is in the Bozeman, Montana drinking water plant. So this is actually where I worked, where I was an operator. So this one was used in a drinking water plant, but it's the exact same concept, exact same purpose as it would be for wastewater. And actually a lot of drinking water plants, they send their like the filter backwashes, or what settles out in the sedimentation basins to a wastewater plant. So the plant that I worked at is a drinking water plant, but we didn't have that ability, so we pretty much had to treat all of our filter backwash and what settles out on site. So we kind of were a wastewater plant in addition to a drinking water plant to an extent. A little bit different though because of what that sediment was and where it came from. But this gravity thickener, this is it it was what received everything that settled out in the clarifiers. And so this gets pumped into the center of this unit. And this looks like a clarifier, and it pretty much is. It works the same way as a clarifier, but as opposed to a clarifier, or it's a little bit different dimension. So this is a pretty small surface area, but it's very deep. So I think this was like 20 feet deep or something like that. So super deep. And whereas a clarifier may not have as thick of a sludge blanket on the bottom, this was actually mostly full of sludge. So it was maybe 75% full of sludge. And the whole idea here is that the sludge gets pumped into the middle, and then it goes out from the middle, and then the liquid goes out through these weirs, flows out, and that's called the supernatant is what that is called. Um, but then the sludge, it settles out because it's heavier than water, so it's more dense. And once that sludge builds up on itself, it becomes thicker and thicker, and it actually compacts the sludge at the bottom. So it uses the weight of the sludge itself to compact that sludge as it goes deeper and deeper down into that chamber, and then it's sucked out regularly from the bottom. Okay, so if we look at our components, okay, so here is what it looks like from a side view. So these are the various components of it. And you can see, like I said, that there's the influent that comes in here through the middle, or to the middle, and then it kind of goes out, disperses from there. Um, Sometimes there's a rake on the top that collects the scum, just like just like just like clarifiers have sometimes. And then the liquid or that supernatant goes out through a weir and then goes out in a trough, and then that usually goes back to the beginning of the wastewater treatment process. And then the sludge, it settles down at the bottom. And then there's this rake that actually spins around, and it kind of works to break up that sludge. And it breaks it up, and the point of that is to release water that gets trapped maybe in some sludge. So it breaks that up so that water can escape, go out those weirs. And it also has a purpose of releasing any gases, because if there's gases that accumulate in that sludge, it'll cause this sludge to float up a little bit and then make it less dense. And the idea is that you want these to be weighing it down. And so the less dense the sludge is, the less efficiently this works. And this definitely happened a few times at the plant I was at. I don't know why, but sometimes you would get there one day and all the sludge kind of just floated up and you weren't really sure why. So have to adjust some processes. So, but it's uh, things like that happen. So, but there's lots of things you can do to make these work better. Okay, so some of the factors that you can think about when you're operating these that are going to change how you operate them. So the sludge type. So we talked about two main streams of sludge coming from the wastewater treatment process. So that primary treatment, so that primary sludge, and then that secondary sludge, the WAS, the waste activated sludge. So this works a lot better with primary sludge because it's more dense. And so that denser sludge, it compacts itself a lot better, of course, because it starts out more dense, and then it uses that weight to compact it. So it works a lot better with that primary sludge. The age of the feed sludge, so the age, like how old that sludge is, that's gonna there's gonna be different amount of oxygen depending on the age, different microorganisms. That's all going to affect how this works. The sludge temperature. So I think maybe I talked about this before, but temperature makes a big difference in all kinds of water and wastewater treatment methods, because temperature really is just a measurement of how quickly those molecules are moving around. So the quicker they're moving around, the higher the temperature, and they're doing their metabolic and chemical functions a lot quicker, more efficiently. Um, and so the higher the temperature is, the more activity you're going to have with those microorganisms. And they're also, the water is less, it is denser the lower the temperature. So that's going to make a bit of an impact too on how well this functions. Okay, and then another factor is that sludge blanket depth. And this is just the thickness of that blanket on the bottom of the clarifier. And um, you can have this thicker or thinner depending on your operations. At where I worked, we varied it all the time and see just to see what works best. And that's going to be dependent on your individual system. And then lastly, it's going to be that the other factors are the solids and hydraulic detention time, so the amount that the solids and the water are in that chamber, and then the solids and hydraulic loading, so the amount of solids and water that is going into that the equipment. So all these are going to have an impact on how this works. Okay, and so if we think about our sludge characteristics, like I said, this works best with primary sludge because it's thicker, and so it compacts better. Um, and then fresh sludge works better than older sludge. It compacts better. That's our point. And then septic sludge, so older sludge, it can have decreased oxygen or even nitrogen in there, and then that can cause this gasification of these metabolic processes that create gases like CO2, methane, hydrogen sulfide. And so you don't want gases being released into this process because gases, of course, are more buoyant. So it decreases the settleability and the compaction of this blanket. Okay, and then just to compare that with the secondary sludge. So like I mentioned, the secondary sludge is less dense and it doesn't settle quite as much. And if you think about this secondary sludge, a lot of that sludge, it really is composed of microorganisms. And so even in those microorganisms, there's all kind of water trapped in those cells. So even those biosolids are mostly water in secondary sludge. So they don't like to compact very, very well. And then those solids are typically finer in the secondary sludge than the primary solids. Okay, and then just thinking about age. So if sludge is held too long, that decreased oxygen may occur. So you have oxygen depletion, and that can cause that denitrification, and again can cause gases to form, which impacts the settleability and the compaction of that. And then also the type of organism. So filamentous organisms, they're associated with older sludge. They can also decrease the settleability and compaction of that. All right, lastly, temperature. So kind of already talked about this, but the increased temperature, biological activity increases. And so that gasification and that sludge rising with those gases can also increase. So, so sometimes these work better in the winter than the summer. Okay, a lot of information on gravity thickeners, and this is a table. I won't go through this, but this is just kind of some parameters of gravity thickener operation guidelines. And one thing I will point out here, though, is that, like I mentioned, these work a lot better with a primary sludge than secondary. And then this is kind of what you can get at the end, that 8 to 10% sludge versus the like 3 or 4% of what got in there. So pretty big increase, but still it's only say 10% solids. So 90% water still. So still a lot of water in there. Big increase, but still lots of water. And then this is just some other parameters. This time is looking at hydraulic loading rate, so the amount of volume or volume per day per square foot for different sludges. And so sometimes you can adjust that with blending your primary and secondary sludge. And if you have higher flows with more liquid, it can kind of prevent some of those septic conditions and odors from developing if you have too old, too compacted sludge. So there's a lot of things you can kind of mess around with these to make them work better. So we're going to do a poll really quick. And so in this poll, so we're going to troubleshoot an issue with the gravity thickener. So say you have a gravity thickener that is experiencing gasification. So that gas is making the sludge rise, so it's decreasing how well that gravity thickener is working. So which one of these following options might help correct the operation of this? And so Matt, if you could throw up that poll. Thank you. And there's two right answers here, so see if you can choose one if you want, or you can choose both if you know what they are. Okay, I'll give you a minute. All right, we'll give you another few seconds, get your answer in. And it's all right if you don't have an answer. We'll go over this. Okay, I'm going to end this poll and share results. Okay, so you should be able to see the results now. And that's great. Yeah, so the correct answers are A and C. So the correct answers are increasing the sludge wasting to lower sludge blanket depth and increasing the recirculation of secondary effluent blended into thickener inflow. So both of those would work to decrease the amount of sludge blanket in there and or increase the amount of like oxygen of sludge going in there. So because the what's happening is it's experiencing gasification and sludge rising. So that's probably due to depletion of oxygen and maybe some nitrification happening, or some septic conditions happening and creating some gases. And then it is not working as efficiently because we're getting that sludge floating up a little bit, not compacting as much. So awesome job. Okay. Okay, so really quick, we're going to talk about this sludge blanket volume to sludge to excuse me. So the SV ratio to our sludge to volume ratio. And so we don't necessarily need to go through this in too much depth, but kind of the main idea is that the ratio you can kind of adjust this depending on kind of what's your parameters of your specific the design for your plant. So this is just thinking about and quantifying the amount of sludge entering versus that blanket volume. And so if you have more sludge entering than is leaving, you're going to increase that blanket volume. And if you have less sludge than is leaving, then you're going to decrease that blanket volume. So these are just some things you can calculate to improve your operations if need be. And so this is just some of the parameters of that. And so this is an example using these parameters, I guess. And so it's kind of nice to be able to know how to do something like this because where I worked, we had that gravity thickener, and I never really thought about calculating any of this or looking at our specs. We would just change things and then see what happens, which is a lot of what you do at a water or wastewater plant. But it's nice to be able to use some of these calculations and then look up what the specs are, what the engineering was designed for in your plant, and that's probably what you're going to go for, what you want to aim towards. Um, so that's something you can do. Okay, and then another thing you can calculate is this efficiency, this removal percentage. And so after your gravity thickener, you are going to have two streams again. So our sludge is coming in, and then we're going to have that thickened sludge coming out the bottom, but we're also going to have that liquid, the water, what's called the supernatant, flowing over these weirs. So you can figure out what the removal efficiency is of that sludge coming in versus what that water is coming out. So you can use this same removal, percent removal equation. And this is something that you can use for all sorts of different removal, or like use it for, like, say you want to remove nitrogen, or you want to remove the total suspended solids or something. You can use the same equation to measure how much you're removing throughout whatever your process is. Okay, so in this example, we want to figure out what our efficiency is, our removal for our gravity thickener that has flow in at 30 gallons per minute at 3% concentration, and then flow out at 0.15% concentration. So we can figure out what our removal percentage is. And I think this is a poll, but I'm just gonna give you the answer because I'm running a little low on time here. So we can figure out what our percent removal is in this equation. And so to do this, what we do is plug in our influent concentration, so our 3%, or we can enter this as 3%, or we can put it in as 30,000 milligrams per liter, and then we subtract our effluent, so that 0.15% concentration, or we can convert that to a milligrams per liter or parts per million concentration, and then we would divide that by our influent, so by that 3%. And so if we plug that into our calculator with those numbers I just described, we come out with 95%. So what that means is 95%, or I should say it this way, that for our sludge coming into this gravity thickener, it's removing 95% of that total suspended solid. So that's pretty good. And so this is just an example that you can see we can calculate this out by having it in milligrams per liter, also known as parts per million, or you can actually just keep it as your percentage and calculate it out like that. You can do either way. Okay, so now we talked about gravity thickener. So that was things that was kind of using the concept of something that's more dense than water, so settles down and compacts. But now we're going to talk about the opposite. Now we're going to talk about flotation. So this is a DAFT, a dissolved air flotation thickener at the drinking water plant that I worked at. So this is what received our filter backwash. And so in this device, the water would come over here at the right, not quite in this picture, but that backwash water with all kinds of sediment was coming in at the right. All these little air bubbles would push up all that sediment up to the top, and it would float. And this was in addition, this did have an additional polymer added to it to help that sediment clump together. And so then that sediment would float up onto the top. And then these rakes would move and they would push it out into a trough, and they'd go out to our drying beds. So that's how these basically work. Here's a side diagram of this. So you can see in this diagram, the flow is coming into the right, and this is added, polymer is added to this too. And then it starts to float up as it gets into here. So then some of the solids ends up floating and is scraped off by these rakes and then out to discharged or to wherever it goes after this step, perhaps into a digester. Or some of the things are still going to settle out. So these often have sludge removal at the bottom as well. So that's how these work. And this works the same concept of like when you open a can of pop or soda and you pour it into a glass, you'll see all these bubbles coming up. And so this is because this can the liquid in there was under pressure. And then once that pressure was released, all these little bubbles, so in this case carbon dioxide, it was released from that liquid and now it's coming out of solution and bubbling up. And so it's creating that kind of fizzy action. It's really the same process that we're talking about here. And it actually is also the same process of pressurization. So a lot of these work with pressurizing that liquid and then releasing it under atmospheric conditions. And then all these bubbles come out and come to the top and do that mechanical action of floating up these particles. Okay, so there's a few different ways that this can work. The one that I just talked about and the one in the photo was this very bottom one, the dissolved air, the pressure flotation. And this is where the effluent is aerated under pressure and then released at atmospheric pressure. So just like a can of pop. And this is by far the most common, but just know that there are other ways that this can operate. This dispersed air flotation. So this is with just like those little aerators, like actually releasing air at the bottom of something. So kind of like your lagoons may have aerators in them. So it's that bubbles coming up. They can just use biological activity to create gases. I don't know how common that is. I don't think super common. They could also use vacuum flotation. And so that is when the effluent is aerated at atmospheric pressure and then it's released under a vacuum. So then so then those gas bubbles come up. But this bottom one is definitely the most common. Okay, and then for that last one, there are three different ways that can work. So this full flow pressure flotation. So this is when that whole sludge stream coming in is pressurized, and then it's released into the DAF unit, and then that creates those bubbles. This partial flow pressure flowation. So this is when some of that influent sludge is pressurized and then released, creating those bubbles. And then lastly, it's when this is called recycled flow pressure flotation. And I believe this is the most common, and this is what we had at the plant I worked at. But this is actually it uses that effluent flow, so that liquid coming out, and then it recycles it back through, it pressurizes it, and then sends it back up with the solids coming in, and that's what creates those bubbles that pushes those solids up. Okay, here's just another photo of the plant that I worked at. So you can kind of see here where that water is pouring out. So the water is going to be the cleanest in the middle of that column. So some of the sludge is going to settle down, some of it is going to float up, and so the water between those is the cleanest water, and that's what flows out. And then that top is raked off, and then that bottom is pumped out as well. And then this is some of this water that flows out, this is what gets pressurized and pumped back to the beginning and creates those bubbles. And this is just a schematic of exactly what I just explained. So this is our effluent is going out here. It gets recirculated back in here and pressurized, and then is mixed back with this flood stream as it enters the DAF. Okay, and here's a video of this. So you can kind of see the rake pushing that top blanket into a trough. And then here on the other side is this the water that's flowing out. You can see that that water is pretty clean. Okay, and for this, you can calculate different operational parameters as well. So this air to solid ratio. So I'm not going to go through the details of this, but just know that you can calculate this based on your system and then figure out if it fits in your design parameters. So here's an example of this, and we'll send out these slides later in case you want an example. Okay, and here's just some operational guidelines for like the capacity and what these can accomplish, depending on if you have them with a polymer or without a polymer. So these are pretty efficient and work very well. Okay, and here's just some troubleshooting techniques. So if you have too thin of a blanket, too thick of a blanket, decrease the speed of your rake, perhaps, to change how much is coming in. Um, good effluent but thin float. So maybe your air to solid ratio is too low. So you can check your air pressure, the amount of air going in. Or if you have poor effluent but thin float, maybe your pressure is too high. So a lot of these things, you can just mess with them, see what happens. It's a good idea to have an idea of what might happen when you just mess with different parameters, but a lot of this is just dialing it in for your specific system and operations. Okay, the next piece of equipment I'm going to talk about briefly is centrifuges. So this is a concept that you're probably all familiar with. So this is like what your washing machine does. After it washes your clothes, it spins all the water out to the side. So it's pretty much the same concept in the wastewater centrifuges. So this is called a solid bowl centrifuge, and this is a video that I'm going to play really quick. Oh, and I will note too that some of these companies have really great videos of their equipment, but this by no means means that we're endorsing that company or anything. They just have nice videos. Okay, so you can see in this that there's this big tube with a corkscrew going through, and so the the wastewater is pumped into the center of this and goes into that corkscrew, and that corkscrew pushes the solids one direction, and then the water goes through the other direction, and then that centrifugal action spins the solids out at the end of here. And so solids come out on one end, water comes out on the other end. And so these are typically they're continuously running, and so they're generally used in larger plants. All right, kind of see how the action going on there, and there's like perforated corkscrew, and then yeah, there's that sludge coming out one end. Okay, there's also these basket centrifuges. So this works a little bit different, but it's the same concept. The sewage is, or that sludge is sprayed, comes into the middle of this, and this is all spinning around. And then the water goes through this basket, a perforated basket, and goes to the outside. And then the sludge stays inside this basket and then is scraped off and then into a hopper or a trough. So same concept, different orientation, and a little bit different function. And you'll see as I go through some of these, there's a million different machines that do the same thing, but they all use kind of the same concepts of filtering out, squeezing, have water going through mesh screens. So it's a lot of the similar processes, but just different machines that do it. Okay, and here are just some parameters for centrifuges. So you can adjust them to do all kinds of things. And these centrifuges are kind of cool because these can both work for sludge thickening and also the dewatering stage. So depending on how they're used in different styles and such. Okay, another piece of equipment. And sorry, I skipped over that last slide, but I think it's more important to go through all these different pieces of equipment. Okay. So this is what's called a gravity belt thickener. So this is pretty similar to a belt press, which you may all have heard of and are pretty common. But this is for thickening as opposed to dewatering. And so this is going to not remove quite as much water, but it's more of a thickening process, maybe before the digestion phase. So in this, there's the sewage is coming in on the left, a polymer is added, and then the sewage or the the sludge is poured onto a conveyor belt that has holes in it, is perforated, and then it goes over all these different like plows that kind of breaks apart the solids, and that allows the water to separate out from the solids, and then it falls through that perforated like mesh conveyor belt into a trough below it. And then the solids um, accumulates at the end and then goes over into a trough. So a lot of machines that do kind of a similar kind of process. Okay, we also have this drum thickener. I kind of like watching these animations, are kind of satisfying, I think. Let's skip through this one. Okay, so in this one, we have our sewage coming in, polymer is added, and it's mixed up. And those then goes into this thickening unit. And this is a big drum, and this kind of reminds me of these big drum like pre-treatment for removing grit separators. So, but basically, it's a big perforated drum or a mesh drum. The water can go through it, and then the sludge accumulates inside the drum and then comes out the other side. Okay. Okay, so there's all kinds of different things that you can that can be used for sludge thickening. We went through a lot of these. I'm going to skip through this, but you can take a look at this later for if you want to know more of what each of these can be good for and the parameters for them. But this really is where it goes into the digestion phase. And Matt's going to talk about this in just a minute, but I'm going to talk about the dewatering phase first before Matt goes into that. Just because this process is very similar to what we were just talking about, kind of an extension of that dewatering process. It's just removing more water from those solids. Okay, so this first one and this equipment that is super common is called a belt filter press. So this is one I think in Texas, but these things are all over, super common. This one I think San Diego Pueblo. So maybe this is some of you some of you may operate these. And so basically what this does, it has this belt that is a mesh belt that the water can go through. And then you can see at the top of this, those plows, like in that video that we saw, it has that same process at the beginning, but then it squeezes that sludge in between two mesh belts and it squeezes it through rollers, so it squeezes out more water. And then those solids get accumulated at the end, and then they get removed through this conveyor belt and then into a dump truck to be disposed of. So here's a nice video. Okay, again, we have polymer mixing in with this. And it flows up here just like it did in the other belt thickener. So then it goes through these plows again and it allows water to separate from the solids and it falls through. But in addition to that other video that we saw, it goes into a secondary process, like I was mentioning. It goes into this this area where it gets squeezed in between these two belts, and then it goes through all these rollers that essentially squeezes the two belts together with a sludge in between, and it squeezes water from that sludge. And this process, these dewatering processes, these remove a lot more water than just the thickening process that we talked about earlier. So as opposed to just a thicker sludge that would go into a digester, this makes it into a solid. So this is what's called cake. Don't eat it though. All right, and then those belts are cleaned off with some water. Okay, and these are all over. So here's one, I don't know exactly where it is, but this is like there's two different processes. This is that first dewatering one, and then here's that belt press over here. This is one in Antarctica. So even in Antarctica, they have to deal with their sewage. Here's just some parameters about that belt press that you can review later if you would like. Some more parameters about that and some more details and how you can troubleshoot it to get different results if need be. But I'm going to move on to talk about our next equipment. This one is called a fan press. So this is pretty simple. This just has a big disc that is perforated, is like a mesh disc with holes. And so then this rotates around and then the stream is pressed against the sewage stream, and the water is able to come through and it rotates around and then deposits the cake at the end. So pretty simple process. There's also these solid bowl centrifuges like we talked about before, but in this time it would make more of a solid cake as opposed to the dewat or the thickened sludge. Again, their basket centrifuges can do this operation. We have these drum vacuum filters, and this is pretty much the same concept, except this time you have a drum with the solids going on the outside of the drum, and then there's a vacuum on the inside that sucks water through a mesh screen into the inside of the drum. Okay, and then a screw press, pretty much the same concept. It's just separating water from that liquid through pressure and through a mesh screen. Okay, and then lastly, and this transitions into what Matt's going to talk about, I guess, with the or at the end with the drying beds almost, is these different very low tech kind of dewatering methods. On the left, we have what's called a geotube or geobag. And this pretty much is a large mesh bag, and then it's filled up with the sludge, and then the water is allowed to just drain out of it. A lot of times these are used for like dredging harbors and stuff. So they'll fill up these bags with what they suck up from the bottom of a harbor, but a lot of wastewater plants use it. I know a plant in Montana that is using these with a very brand new plant because they even the designs for the plant it didn't adequately address the sludge dewatering. So they're having to buy these, filling them up, dewatering them, and then a company comes and hauls these away. And then over here on the right, we have what's called these phase separator dewatering units. And this is pretty much what it looks like. It is a dumpster that is filled up with sludge, and it has um, some drains at the bottom. And basically, the water drains out at the bottom, and then the sludge is left in these dumpsters, and then those dumpsters can be picked up by a truck and then hauled away. So pretty low tech, um, pretty simple way of doing things. Probably only useful though if you have a pretty small operation. Matt.
All right. Well, I just wanted to thank Tucker for his excellent overview on sludge thickening and dewatering. If you have any questions on what Tucker covered, go ahead and put those in the chat and we'll find time to answer them. Good afternoon. My name is Matt Ziegler, and for the rest of our webinar, I will be covering anaerobic and aerobic biological digestion and processes, as well as land application of solids. So this process is called biological digestion because microorganisms are used to further treat the sludge produced in different treatment processes throughout a wastewater treatment plant. Like many other microorganisms utilized in wastewater treatment, microorganisms used in digesters are naturally occurring in wastewater, and they're manipulated to meet treatment goals. And so the primary goals of biological digestion in wastewater treatment, whether aerobic or anaerobic, include reducing its volume, stabilizing for odor control, and inactivating or killing pathogens to make it safe for disposal or reuse. These goals are achieved through different mechanisms that produce a variety of benefits, including the production of biogas in the case of anaerobic digestion and nutrient removal with aerobic digestion. And so the microorganisms in both anaerobic and aerobic digestion break down the organic matter present in sewage sludge into simpler compounds. This reduces the sludge's organic content and leads to that significant reduction in sludge volume. Organic sludge also has water molecules that are bound up within it, and the digestion process is where most of the water-bound inorganic matter in sludge is released and can be removed as that supernatant. Stabilization means that the sludge is less likely to decompose or produce offensive odors after disposal, and it is less prone to further decomposition that results in foul odors, creating a more acceptable and less offensive end product. Another desired outcome of digestion is to help kill or inactivate those harmful pathogens, such as bacteria, viruses, or parasites that are present in the sludge, making it safer for handling and disposal. Wastewater treatment plants employ anaerobic digestion, generate biogas that can be repurposed. The biogases produced are primarily methane and carbon dioxide, and this biogas is collected and used as an energy source, reducing energy costs for wastewater treatment facilities. Aerobic digestion also has a unique goal.
of nutrient removal. The process can remove nutrients like nitrogen and phosphorus, which can be useful in reducing nutrient pollution in receiving waters when the treated sludge is applied to the land. Achieving digestion goals results in a number of benefits. So again, that digested sludge often has improved dewatering characteristics like we already talked about, and allows for more efficient and cost-effective dewatering processes. This results in further reduction of sludge volume and facilitates subsequent handling and disposal. It means mechanical dewatering, which Tucker covered earlier, is more easily accomplished. In this same train of thought, successful digestion positively affects the end product, which is often referred to as biosolids, which are more stable, less hazardous, and less odorous than untreated sludge. Biosolids can be used in agriculture as a soil conditioner, in land reclamation projects, or incinerated with reduced environmental impact. And that's not the only positive environmental impact that proper digestion results in. By reducing that sludge volume and improving its characteristics, digestion processes help to minimize the overall environmental impact of sludge disposal. This can include reduced greenhouse gas emissions, lower landfill usage, and decreased risk of groundwater contamination. Before we discuss digestion in more detail, we need to touch on what exactly is being digested. Sewage sludge used in digestion can originate from various sources within the treatment process, as Tucker has told us. Each process produces different types of sludge with its own characteristics. And so primary sludge is generated during the primary treatment phase of wastewater treatment. In primary treatment, that raw wastewater undergoes those physical processes like screening and sedimentation to remove the larger solids and settleable materials. The sludge that settles out during the sedimentation is called primary sludge, and it's unstable, odorous, and full of pathogenic bacteria. It's typically 4 to 5% total solids with 70 to 90% volatile matter. Volatile matter is the material available to break down during digestion into simpler components like methane and carbon dioxide. Next, there is secondary sludge, which is produced during the secondary treatment phase. Secondary treatment involves the biological removal of dissolved and suspended organic matter using microorganisms. The excess biomass generated during this biological treatment process, known as activated sludge, is separated from the treated wastewater in the same way as primary sludge through sedimentation. Secondary sludge, it's partially stabilized already. In many cases, primary and secondary sludges, we combine them together to create a mixed sludge, which is then subjected to digestion. Combining these two types of sludge can balance the characteristics and enhance the overall digestion process. Finally, there is tertiary sludge, which is similar to secondary sludge. In some advanced wastewater treatment plants, a tertiary treatment phase may be employed to further improve water quality. And Tucker talked about some of these already. Tertiary sludge may be generated as a result of this treatment, which could include additional stuff like that chemical coagulation, filtration, or nutrient removal. Examples of tertiary sludge include the products of the dissolved air flotation, DAF, and rotary drum thickeners, which is secondary sludge that has been dewatered. Now that we know the basics of digestion and sludge and what it is supposed to accomplish, reducing the volume by breaking the sludge down into simpler components like carbon dioxide and methane, let's look at the details of our first type of digestion, and anaerobic digestion. And this is where we will cover the steps and chemistry of the process of anaerobic digestion, as well as the components of the digesters and their operation and troubleshooting. Okay, so anaerobic digestion, it's a biological process, again, like any type of digestion, and it takes place in the absence of oxygen. And it's widely used in wastewater treatment for the stabilization of sewage sludge. anaerobic digestion, it relies on those two groups of bacteria living together. And so we have to remember about the saprophytic bacteria. These are the acid formers. And then the other type are the methanogens. Methanogens, they're not as abundant and they require very specific conditions to reproduce and need a pH range of 6.6 to 7.6. Anaerobic digestion occurs in multiple steps that we will look at in detail. The important byproducts of the anaerobic digestion process, again, are the methane, the carbon dioxide, and then that water that we're trying to take out of the sludge. And so let's look at those specific steps of the process. And so the first step in anaerobic digestion is hydrolysis. In this step, hydrolytic bacteria are responsible for the initial breakdown of complex organic compounds into simpler soluble substances. They secrete enzymes that hydrolyze large molecules such as proteins, carbohydrates, and lipids or fats into smaller components, making them more accessible to other microorganisms in the anaerobic digestion process. Next, we have acidogenesis, which has a few different mechanisms, but the overall goal is to further metabolize the intermediate components from hydrolysis into volatile fatty acids with acid-forming bacteria, also known as fermentative bacteria. They further metabolize the products of hydrolysis, producing organic acids, alcohols, and other fatty acids. In our next step, during acidogenesis, we have the intermediate products from hydrolysis and acidogenesis are converted into acetate, another volatile acid produced by the acidogenic bacteria. This conversion, it's a crucial step in anaerobic digestion as acetate serves as a key substrate for the next group of microorganisms, the methanogenic archaea. And the methanogenic archaea, they're responsible for the final step in anaerobic digestion, where they convert acetate, hydrogen, and carbon dioxide produced in the previous stages into the methane and carbon dioxide, into those biogases. This unique group of microorganisms belong to the archaea domain and are primarily responsible for producing that biogas. They have been shown to be genetically different from bacteria, but are also single-celled microorganisms. So temperature plays a big role in anaerobic digestion, and we have three distinct temperature ranges. We have the psychrophilic, the mesophilic, and the thermophilic range. And all of these take advantage of different groups of bacteria to aid in the anaerobic digestion process. The choice of temperature for anaerobic digestion really depends on several factors, including the type and characteristics of the organic material, the desired biogas production rate, the specific microbial community in your system, and the energy and heating costs associated with maintaining the temperature. It's important to maintain stable temperature conditions for all of these ranges throughout the process to ensure the optimal performance of the microorganisms and to avoid any temperature fluctuations that can disrupt the digestion process. So temperature is super important. And when we look at the psychrophilic anaerobic digestion, this takes place at cold temperatures, typically between 50 to 68 degrees Fahrenheit. And it's accomplished by cold-loving bacteria in cold climate regions, or for the treatment of low-strength wastewaters or sludges that can't be easily heated. Psychrophilic digestion produces hydrogen sulfide and water byproducts, as well as a little bit of methane. While the biogas production rate's slower and less effective in psychrophilic conditions, it can still be a viable option when higher temperatures aren't feasible. Examples of digesters in this range are Imhoff tanks, septic tanks, unheated unmixed digesters, and the anaerobic portion of lagoons. Next, the mesophilic anaerobic digestion takes place at those medium temperatures, typically 68 to 113 degrees Fahrenheit, with an ideal temperature range of 95 to 98 Fahrenheit, which is similar to human body temperature. This type of anaerobic digestion is accomplished by medium temperature loving bacteria, the mesophils. Mesophilic conditions support a balanced population of microorganisms, resulting in efficient biogas production and organic matter degradation. Mesophilic anaerobic digestion is the most common used in wastewater treatment plants and is suitable for a wide range of organic materials. Again, thermophilic anaerobic digestion takes place at the higher temperatures, typically between 120 and 135 degrees Fahrenheit. This type of digestion is accomplished by heat-loving bacteria, the thermophiles. This temperature range can accelerate the digestion process and increase biogas production rates, and is particularly effective at destroying pathogens and can be used to treat more challenging organic materials. However, it requires more energy to maintain that higher temperature, and some microorganisms may be less competitive under these conditions, resulting in that poor liquids and solid separation. Standard conditions for anaerobic digesters can vary depending on the specific design, purpose, and the type of material being treated. Since mesophilic temperatures are most commonly used, we're going to refer to the preferred parameters for mesophilic conditions from this point forward in the webinar. There are several key operational parameters that are commonly monitored and controlled in anaerobic digestion systems to ensure efficient and effective performance. These include temperature, detention time, pH, and volatile acid to alkalinity ratio. As previously stated, the ideal temperature range for mesophilic conditions is 95 to 98 degrees Fahrenheit. The detention time for anaerobic digesters should typically be between 25 and 30 days. The recommended pH for anaerobic digesters, as previously mentioned, is the 6.6 to 7.6 range, but the optimal range of 6.8 to 7.2 will ensure ideal conditions for the methanogens to do their job. Finally, the volatile acid to alkalinity ratio should be 1 to 10. This is because alkalinity, often measured as total alkalinity or bicarbonate alkalinity, helps buffer the pH and maintain a stable environment for microorganisms. In this environment, adequate alkalinity levels, typically 1,500 milligrams per liter as calcium carbonate, are crucial for maintaining digester stability. And we'll talk a little bit more about that in a few slides. So the different parts of an anaerobic digester, the digester tank seen here in this diagram and up here in this picture at the Albuquerque-Bernalillo County Water Utility Authority at their wastewater treatment plant is the primary vessel where anaerobic digestion occurs. It's typically a sealed and insulated container made of materials like concrete, steel, or fiberglass reinforced plastic. It's designed to maintain anaerobic conditions, preventing the entry of oxygen. Tanks are cylindrical and about 20 feet deep, with sloped floors so that sand, grit, and heavy sludge can be withdrawn, as well as transfer seed sludge to a primary digester or pump it to drying beds or a dewatering facility, or to recirculate bottom sludge and break up scum blankets. Next, sludge lines. They're essential in managing sludge volumes in the digester because we have to move stuff around a lot. Sludge feed lines feed into the top of primary digesters opposite where the supernatant or overflow line would be. They also can be injected into a sludge recirculation line upstream of that heat exchanger. Discharge lines are located at the bottom of slope digester tanks. And these draw-off lines should be a minimum of 6 inches in diameter to allow for adequate discharge, and they're equipped with plug valves, which do not get fouled with debris or rags like a gate or a butterfly valve would. Heat exchangers are used to heat sludge that is recirculated to the digester to perform temperature control and maintain the digesters at the desired temperature. Mixers, right here, you can see, speed up the breakdown of those volatile solids, and they increase methane production. Fixed covers are used on primary digesters, and floating covers are used on secondary digesters to provide flexible space for gas storage. They move up and down depending on the sludge and gas levels. The interior is sealed off from the atmosphere by a sludge seal between the cover and the digester wall. If level drops too low and that seal is broken, you can get methane mixing with oxygen, and that could become explosive. Other anaerobic digestion components or digester components include a digester gas system to manage and collect the biogas produced in the anaerobic digester. The gas system is used to remove gas to a point of use, provide safety features, and burn off excess gas in a waste gas burner. We have flame arresters as a safety device designed to prevent the propagation of flames and explosions back into the biogas handling and storage system. It prevents flames from traveling backwards. Some digesters use supernatant lines to remove supernatant from the digester with the lowest solids and transfer it to the headworks or primary clarifiers. This process should be carefully managed because high nitrate and BOD content in the supernatant can cause issue with the other treatment processes. Sample ports are pipes with hinged lids that extend into the digester below the gas layer, or overflow boxes off the recirc lines, and are used to collect samples for process analysis. They are used to sample sludge at the top of the digester or from the recirculation lines. Lastly, digesters should have pressure release valves, which are also known as safety release valves or pressure safety valves. This prevents overpressurizing the system if it exceeds a predetermined set point. Once open, the valve allows excess gas to be safely vented to the atmosphere or to a controlled flare system where the gas can be safely burned off. The valve then closes when pressure returns to a safe level. The specific design and configuration of anaerobic digesters can vary based on the size and type of your wastewater treatment facility, the treatment goals, and available resources. Proper operation, maintenance, and monitoring of these components to ensure effective anaerobic digestion and safe operation of the digester is super important. Now that we know about the different parts of the digester, let's talk about operating anaerobic digesters. So in the mesophilic range, digestion occurs in two stages, primary and secondary digestion. So in the primary stage, sludge is heated using heat exchangers, and then it's mechanically mixed. Up to 90% of gas production happens here. These digesters use fixed covers, as already stated. During the secondary stage is used for storage as well as solid liquid separation. This is where floating covers are used to accommodate both fluctuations in sludge volume that's being treated in the system, as well as gases. It is the secondary digester where supernate is sometimes returned to the primaries or headworks, as we mentioned earlier. And as we mentioned earlier, this water is usually high in nitrate and BOD, so the process needs to be managed. The secondary digester also serves as a source to reseed a primary digester if it becomes upset or sour. Finally, secondary digesters are sometimes mechanically mixed, but it is not an essential part of it, like it is with primary digesters. As with many wastewater treatment processes, it's important that operators have a strong understanding of your pipe alignments. Digester lines are complex to allow for transfer as needed, and it's important to avoid any confusion with this process. Successful anaerobic digestion operations revolve around maintaining the balance of those acid formation using the saprophytic bacteria and the methane fermentation through methanogenesis. So to do this, it's again important to maintain the ideal temperature and not change that temperature more than 1 degree Fahrenheit per day. Really, those organisms need a time to adjust to the conditions, and large fluctuations in temperature can impact that process. Proper mixing in the digesters is also important to maintain a balanced system, to ensure even heat distribution and keep the microorganisms in contact with the food that they need to do their jobs. Proper sludge feeding is important, as well as withdrawal rates. You need to maintain them in accordance with design specifications, because we don't want to overfeed sludge. Because that overfeeding can increase the volatile acid content of the digesters. That's going to increase that volatile acid to alkalinity ratio. And you'll recall this ratio should be 1 part volatile acids to 10 parts alkalinity under ideal conditions. You know, sludge feeding, it's going to be much more detailed than new operators tend to realize. It should be a well-mixed combination of both raw sludge from primary clarification and partially digested secondary sludge from biological and wasting processes, such as the dissolved air flotation and the rotary drum thickeners. That's really due to the two, to what the differences are in those two types of sludge. And so with raw sludge, or primary clarifier sludge, it typically contains 4 to 5% total solids, of which 70 to 90% is volatile matter, which is digested rapidly. Wasted or secondary sludge after biological treatment ranges to 0.2 to 4% total solids without a polymer. If you use a polymer, then it's going to be 3 to 6% total solids and contains 65 to 75% volatile matter, which leads to slower digestion in the raw sludge. And so when we do digestion, we really want to have a mix of both of these sludge types to make sure the digestion process is adequate and we get the product that we're expecting. With sludge feeding, we want to make sure to do it several times a day. One, to avoid lowering temperatures, but also to avoid overfeeding. This helps keep primaries from holding too much sludge for too long, and really ensures the thickest sludge possible is being fed into the digester. Again, sludge should be as thick as possible because, one, like Tucker talked about, it takes up less space in the digester, but it also ensures that we don't introduce too much water into the process. If sludge contains too much water, it dilutes the digester's buffering capacity. Buffering capacity, that's the ability to neutralize the organic acids produced by the acid formers, and really depends on the alkalinity within the digester sludge. If there's not enough buffering capacity, the pH is going to drop and the digester is going to become sour. A change in the volatile acid to alkalinity ratio, if you're monitoring that, provides the first indication that something is wrong with the digester. Sludge rate withdrawal should not exceed 5% of digester contents in a 24-hour period, again, to avoid upsetting those microorganisms. So again, you need to monitor the process to make sure that you're meeting all of those parameters. And so to operate these digesters correctly, it's important to look at these key parameters. So again, as we've talked about multiple times, it's important to monitor the temperature of the digester to keep it in the ideal temperature range and to ensure that you aren't changing that temperature by more than 1 degree Fahrenheit per day. You usually measure temperatures in the sludge recirculation line and at the heat exchangers. This is because it's best to monitor temperature as the sludge is leaving the digester and the temperature of it after heating, and it's being recirculated back into the digester. It's also useful to monitor the temperature of the water being used for heating so you can understand how that may impact changes to sludge temperature. Sludge samples should be analyzed in the lab multiple times a week to establish that volatile acid. and alkalinity concentrations to ensure the 1:10 ratio is not exceeded. You should also monitor biogas content. The methane to carbon dioxide ratio for a good digester gas should be about 65 to 70% methane and 30 to 35% carbon dioxide. If CO2 levels exceed 42%, the digester is not operating well. And at a 45% CO2 level, the gas is not going to combust or burn. Hydrogen sulfide gas levels should be less than 5%. When you analyze the volatile acid and alkalinity concentration, it's also a good idea to measure pH, which we previously mentioned should be in the 6.6 to 7.6 range. And then finally, it's important to analyze for the total solids concentrations, which should be determined for feed sludges, your recirculating sludge, your withdrawn sludge, and your supernatant. Typical digester sludge is 3 to 6% total solids content with a volatile solids reduction of 50 to 60%. Finally, to go along with operations and analysis, we'll talk a little bit about digester issues and troubleshooting. The first problem we'll discuss is digester souring. This is indicated by a volatile acid to alkalinity ratio that's greater than 0.1 or 1 to 10, and a pH range that has dropped to 7.0 to 7.2. It's frequently caused by excessive raw sludge feeding, causing the acid formation to exceed the methane fermentation, or the sludge withdrawal rate is too high. The excessive acid will inhibit the activity of those methane producers. Remedies are to pause feeding and recirculate secondary digester sludge to the primary digester to increase alkalinity and reseed good organisms. A digester may also become stuck. This condition is indicated by a volatile acid to alkalinity ratio greater than 0.5 and a pH below 7.0 and dropping. It is caused by not correcting a souring digester. So if you don't take care of it, your digester is going to become stuck. Remedies are again to pause the feeding, to stop the production of more acid, and to add alkalinity by adding lime, calcium hydroxide, or soda ash, sodium bicarbonate. Both will neutralize the organic acids and get your alkalinity or your volatile acid to alkalinity ratio back where you want it. Then there is foaming, which is indicated by large amounts of foams and sample ports, overflow boxes, or out the digester lid. Possible causes are just side effects of starting up a digester, or if you're breaking up a scum blanket, which is kind of unavoidable. You may also have radical temperature changes that can cause foaming, or if you are overfeeding. Remedies are to increase mixing, stop or lower your feeding rate, and to stabilize the temperature. Some more troubleshooting tips. Low methane production is assessed by monitoring biogases and is indicated when the CO2 concentration is greater than 40%. Low methane production can happen during the startup period for the digester, if you're underfeeding, or if there is uneven temperature control. Remedies are stabilizing temperature as well as controlling feed and withdrawal rates. Finally, the last troubleshooting topic we're going to talk about is when there are large amounts of suspended solids in the supernatant. This condition is indicated by a total suspended solids concentration that's greater than 1,000 milligram per liter. And this is caused by drawing from wrong level in the digester or excessive increases in temperature. The remedy is to simply adjust where supernatant is drawn from or limit excessive heating of that recirculated sludge. So one of the important byproducts of anaerobic digestion is producing this biogas. And so you have to have a collection system to collect that biogas. And so this system is composed of a gas dome up on top here, pressure and vacuum relief valves. It's got flame arresters. We have thermal valves, sediment traps, drip traps, gas meters, a manometer, pressure regulators, and a waste gas burner. And And so when we are producing biogas, you're getting 8 to 12 cubic feet produced for every pound of volatile matter that you're adding to that anaerobic digestion. And you're going to get 12 to 18 cubic feet produced for every pound of volatile matter that you're destroying. Because of this, because biogas has a heat value of 500 to 600 British thermal units, or BTUs per cubic foot, it can be used for heating the digesters. You can also drive generators for electricity at the plant, and you can also use it for heating buildings. Well, that was a broad overview of anaerobic digestion. If you have any questions about what was covered, put them in the chat and we'll make sure they get answered. The other type of digestion is aerobic digestion, which we're going to talk about right now. So aerobic digestion, as the name suggests, is the opposite of anaerobic digestion and occurs in the presence of oxygen. It is another biological process used to further treat sewage sludge, particularly after anaerobic digestion. It's not as widely used as anaerobic digestion because it's more energy intensive, but it's gaining popularity for its ability to provide additional sludge stabilization as well as that nutrient removal. Aerobic digesters can be thought of as an extension of secondary treatment processes. They are typically seen in small to medium-sized plants that utilize extended aeration, activated sludge, and sequencing batch reactors, or SBRs. Solids are held in a tank. They're provided air and mixing with no artificial heating. Because there is no food source, the organisms eat each other. They devour each other. This is known as endogenous respiration, where organisms metabolize their own cellular matter because there is no external food source. This process results in a breakdown of the sludge with the release of carbon dioxide and water vapor. Pathogens are reduced because of predation from a wide variety of microorganisms. Aerobic digestion is not as efficient as anaerobic digestions, and so we only see a volatile solids reduction of about 20 to 40%, but overall detention times can be somewhat shorter at 20 to 30 days. Aerobic digesters, they're very similar in construction to anaerobic systems, but often at a smaller scale. Like anaerobic systems, they have digester tanks to hold sludge, but these are shallower at about 10 feet deep. They also have aeration systems to maintain the system's dissolved oxygens. These systems can use floating surface aerators, fixed bridged aerators, or blowers using coarse bubble diffusers. Just like anaerobic digesters, sludge inlet lines come into the top of the digester above the tank's high water level, with outlet lines located at the bottom or sunken in a sump on the digester floor and are used for emptying and for maintenance. Lines should be a minimum of 3 inches in diameter. Supernatant tubes are widely used to remove decanted liquid off the top of the sludge and return it to the headworks. To remove supernatant, it has to be shut off to allow sludge to settle to the bottom. It's important to keep in mind that supernatant can be a source of filamentous bacteria. As we learned previously, filamentous bacteria, they can serve as a structure for other bacteria to attach to and form flocks as part of the flocculation and settling process. However, an excessive number of filamentous bacteria may cause problems with sludge settling, bulking, and foaming, and have an impact on wastewater treatment efficiency. Aerobic digester operations are simpler than anaerobic digesters because not as many issues can arise with fewer moving parts and fewer process control monitoring requirements. Feed rates aren't as critical, and really they're based on the need to remove solids from the secondary treatment process. So you feed it when you need to remove solids from the secondary treatment process. It's the same thing for sludge removal rates, which are determined by their level in the digester and the availability of sludge dewatering and drying units. So when you need to remove sludge and you have available equipment, then you can go ahead and remove it from the aerobic digester. As with secondary treatment processes, it's important to maintain a dissolved oxygen of 1 milligram per liter or the digesting sludge will have odor issues. Some would describe the smell like a rotten melon or worse. Digesters need to be taken offline and cleaned at least every 3 years to remove sediment buildup and to inspect equipment inside the digester. Just like anaerobic digestion, there are some important parameters that should be monitored in the aerobic process. First, the pH of aerobic digesters should always be greater than or equal to 7.0. If the pH drops below 7, there's going to be a problem in the secondary treatment process, such as nitrification, which causes the wasted sludge from the secondary process to become acidic. If this occurs, adding a source of alkalinity to the digester, like lime, will increase the pH. Total solids content of the sludge should also be monitored. For the feed sludge, you should monitor the digester sludge and the withdrawn sludge. Sludge in aerobic digesters should have a total solids range of 1.5 to 4%. Volatile solids reduction should be monitored in the 20 to 40% range mentioned earlier. Reductions of these solids indicates the effectiveness of the aerobic digestion process. And over time, the volatile solids reduction is going to decrease due to buildup of sediment in the digester. If you see this, this indicates the detention time is decreasing and the digester needs to be taken offline and cleaned. Finally, there is dissolved oxygen, which we mentioned earlier, should be maintained at a concentration of 1 milligram per liter and should never be allowed to drop below 0.5 milligram per liter to avoid odor issues. Well, now that we have stabilized and reduced our solids through primary and secondary treatment processes and digestion, we are going to look at how to get rid of those solids through land application. The precursor of land application are drying beds, which are used as an alternative to mechanical drying processes that Tucker already talked about. There are 3 types of drying beds. There's sand, asphalt, or concrete, and there are vacuum filter beds. The one shown in the picture is a sand drying bed at the city of Albuquerque right here that's not used anymore. Drying beds are limited to small to medium-sized plants. They handle less than 5 million gallons per day because they require a lot of land. Warmer climates are also better suited for drying beds as higher temperatures aid with the drying process, and frozen sand drying beds have to be thawed before you're able to clear them. Here's some examples of some drying beds. Here, the picture at the left is at the Bozeman, Montana treatment plant where Tucker worked, and includes cement with a sand trough down the middle with perforated pipe. The picture on the right is at the city of Espanola, New Mexico, where sludge has dried to a point where it will be used for land application or composting. So a sand drying bed includes a shallow line concrete or earthen basin, and it has a perforated pipe that's installed under a 12 to 18-inch layer of gravel with 8 to 12 inches of sand on top. Decant tubes are going to be located on the corners of the drying bed to drain pooled water from the sludge. And drying is accomplished through water evaporating up from the sludge while also percolating down through the sand layer where it's collected and removed by the perforated pipe under drain system. Condition of the sand layer is important. It has to be level. Older drying beds that can become compacted and they're not going to allow water to permeate. And if this happens, you got to remove the top 2 to 3 inches of sand and replace it with fresh sand. Some beds use expensive pre-wash sand and others use arroyo sand. The best sand has no dirt or clay, and it's going to be free of excessive small particles called fines. Sand drying bed operation. So as mentioned previously, those frozen sand drying beds can only be cleared when thawed. Sludge should be poured onto the drying bed to a depth not to exceed 12 inches, or drying time will increase substantially. Also, new sludge should not be poured on partially dry sludge. This is known as capping, and it's going to cause the lower layer of sludge to get sealed off, and it's going to turn into something called green sludge. And green sludge is really odorous, and it's not, and it's not going to dry. If you use polymer, it's going to cut that drying time in half. And when the sludge has dried and cracked all the way through to the sand, It is removed by shovel, or if a skid loader is used, care has to be taken not to crush that under drain system. Managing this process effectively can produce greater than 95% total solids. Next, we are going to look at asphalt or concrete drying beds. These drying beds function just like sand drying beds, but instead of sand, asphalt or concrete is used as the surface on which the sludge is applied. The hard surface allows the sludge to be mixed with a tractor or backhoe or specially designed equipment, which really speeds up that sludge drying time. And because of this, sludge can be poured to a deeper depth of 18 to 30 inches. Due to that sludge depth, decant tubes are really important for removal of surface water in this case, because evaporation alone would take too long. Decant tubes are, Finally, we're going to look at vacuum filter beds. These beds consist of a shallow concrete basin with an underdrain system covered with porous pumice bricks or stainless steel or plastic perforated panels. Sludge is conditioned with polymer before being put into the bed. A vacuum pump is used to create a vacuum underneath the panels, which rapidly draws water from the sludge. And so this process can produce sludge with 15 to 30% total solids in a matter of hours or days. So it can rapidly dewater that sludge. And also the filter bed can be cleaned by a skid loader or a small backhoe, and really decreasing the man hours needed to maintain them. So let's talk more about land application of biosolids, and it involves applying biosolids to vegetated land to create compost that adds nutrients to the soil. And when adding solids to the land, there are three areas of concern. And so pathogenic contamination is one of those concerns, and we measure it by measuring fecal coliform, which is used as an indicator organism. VAR, or vector attraction reduction, is also an area of concern, and it really indicates what measures you've taken to minimize the attraction of nuisance species. And lastly, toxins or potential toxins such as heavy metals, PCBs, polychlorinated biphenyls that are used in electrical equipment, and nitrogen compounds are of concern. The law that governs disposal and use of sludge is Title 40 of the Code of Federal Regulations, Part 503, which sets out treatment techniques to reduce pathogens and adhere to vector attraction reduction and heavy metal requirements. There are two classes of sludge that are regulated here. Class A, it's a high quality sludge that can be sold or given away to the general public. And Class B is a lesser quality sludge that can still be land applied when specific management practices are followed. So we're going to look at both classes of sludge in a little bit more detail. Class A has strict composting requirements, and composting is a thermal aerobic biological practice similar to aerobic digestion that breaks down compounds into nutrients. Sludge is placed in a pile called a windrow, along with wood chips or other mulch green waste. Microorganisms digest the sludge and green waste, and those windrow piles have to be mechanically aerated or turned to provide oxygen to keep aerobic organisms active. Microorganism activity creates heat and temperatures greater than 131 degrees Fahrenheit, which must be maintained for 15 days with 5 complete pile turnings done within that time. To apply biosolids to land, a special compost facility operator license is required. Surface disposal is regulated by Title 40 CFR 503, and it involves restricting the maximum amount of heavy metals and other toxins that can be applied to the land for all time, as well as making sure vector attraction reduction practices are employed. A permit is required from a regulatory body such as the New Mexico Environment Department's Groundwater Quality Bureau here in New Mexico. It's going to be different for your states. Sludge can also be injected as a liquid 1 to 3 feet below the surface, or it can be spread as a solid over land and plowed to mix into the soil. Surface disposal of sludge in this manner is not considered as environmentally friendly an option as land application. Finally, landfilling is the least desirable option for sludge disposal. It takes up valuable landfill space and should only be practiced if the sludge is of poor quality or due to economic limitations. Landfilling of sludge requires a sludge disposal plan approved by the appropriate regulatory agency. And sludge haulers, they have to be licensed with a special waste permit to transport that sludge.